The universe has no outside. Some might argue, if the universe is expanding, it must be growing into something larger. But the expansion isn't matter moving into pre-existing space. Space itself is generating new space. So in the next few minutes, we will trace this concept from Hubble's redshift to the microwave background in TV static, from the early universe the size of a beach ball, to Einstein's so-called greatest blunder, the cosmological constant. In the end, you may realize our idea of an outside might be an illusion we can never reach. A simple analogy to make cosmic expansion easier to grasp. Let's start with a simple scene. Imagine inflating a balloon in your living room. Air rushes in, the rubber stretches, the balloon occupies more space. It can grow because there's room around it. Your living room is its outside. Naturally, we assume cosmic expansion works the same way. Space seems to be expanding into a larger cosmic room. If it's growing, it must have edges. It must have an end. This seems logical, but it's a cognitive trap. Physics tells us the universe doesn't work that way. The true nature of expansion, when space expands, it isn't pushing into an external void. There is no outside, no container, no emptiness waiting to be filled. The universe, as it grows, generates its own space. A better analogy: if you want to draw a circle larger than your paper, you don't find a bigger sheet. You make the paper itself grow to accommodate the line. This sounds strange because in daily life, all expansion happens into something. Plants grow into air, cities expand into countryside, ice spreads over water. We instinctively understand the world in terms of inside and outside. But if you are the paper in the drawing, the concept of outside loses meaning. So the question shifts, not where is the universe expanding to, but how do we know space itself is growing? Evidence from starlight. The answer comes from the most distant starlight. By observing far-off galaxies, scientists uncovered this counterintuitive truth. Edwin Hubble found the farther away a galaxy is, the faster it recedes. At first glance, this suggests we're at the center of a cosmic explosion, as if everything is flying outward from here. But the real surprise, galaxies aren't moving through space. The space between them is stretching. A reversed balloon analogy makes this clear. Think of galaxies as dots on the balloon's surface. As the balloon inflates, the dots move apart. But the dots aren't crawling, the surface itself expands. Every dot sees the others receding, and no single dot is the center. Replace this 2D surface with our 3D space, and you reach the key conclusion. The universe isn't expanding into somewhere outside because there is no outside for it to enter. It is growing while generating its own stage. Even Einstein struggled. This conclusion baffled audiences and geniuses alike. Even Einstein initially resisted. Yet this seemingly impossible expansion is happening right now at unimaginable speeds. But how do we know this isn't just a pretty metaphor? Cosmological redshift, the proof. When a distant galaxy emits light, its wavelength is fixed. Blue, red, or infrared, each has its fingerprint. But as this light travels through expanding space, its path stretches beneath it. Imagine walking on an extending moving walkway. Your stride remains the same, but the ground lengthens silently. By the time you reach the end, you've covered more distance. For light, the result isn't greater distance. Its wavelength stretches. So blue light from afar reaches us as red. Crucially, this isn't the Doppler effect from an ambulance siren, but space itself stretching during the journey, widening the gap between each wave peak and trough. This is cosmological redshift, direct proof that space itself is growing, independent of the motion of objects within it. A mind-boggling scale. The most distant observable galaxies have their light stretched nearly 40-fold. Intense ultraviolet has been pulled into faint infrared. This means during its billions of years journey, the universe's scale grew nearly 40 times. Thus, the galaxy you see in telescopes small and dim was much closer when its light began its journey. Space isn't just growing slightly, it's undergoing a sustained, magnificent stretch. Expansion is everywhere. Crucially, this stretching isn't confined to some distant corner. It's happening everywhere. The space in your room is trying to grow. The space between your eyes and this screen is attempting to stretch. You don't feel it because electromagnetic forces between atoms hold matter firmly together. On this scale, expansion's force is negligible. Only between galaxies, where atomic bonds are absent, can expansion freely play out, carrying them ever farther. It's like raisins in rising dough. The raisins aren't actively moving. The dough itself is expanding. So when you ask where the universe is expanding to, you're asking where the dough is going, forgetting you yourself are part of the dough. The cosmic horizon. Since space is stretching everywhere, how far can we see? To be blunt, we live in an invisible cosmic prison, whose walls are built by time itself. When you look at the night sky, you might think the entire universe is spread before you. But the truth shatters this perception. What you can see is likely less than 4% of the real universe. The reason is simple yet brutal. The speed of light is finite. The universe's age is finite. The farther you look, the deeper into time you see. Looking at the sun, you see 8 minutes ago. At Alpha Centauri, 4 years ago. At Andromeda, 2.5 million years ago. The universe is about 13.8 billion years old, meaning the oldest light has traveled at most 13.8 billion years to reach you. Galaxies beyond this are, from your perspective, non-existent. Their light is still en route. But remember, during this time, space is kept expanding. Those distant galaxies were much closer when they emitted the light we receive today. By the time this ancient light arrives, expansion has carried them 46 billion light years away. So our observable universe is a bubble about 46 billion light years in radius. Outside this bubble lie more galaxies, stars, and perhaps another version of you reading these words. You can't see them not because they aren't there, but because their light hasn't had time to arrive. Thus, everything beyond the bubble becomes the unobservable universe. This isn't a physical barrier, but a limit imposed by physics. You can think of it as a thick fog, restricting your view in every direction to a certain distance. You know there's a world beyond the fog, but you cannot penetrate it. The oldest light. To understand this time wall, we must look back at the oldest light. The oldest light in the universe today races toward you at 670 million miles per hour. It is older than our solar system, older than the Milky Way's formation. Its journey began when the universe was just 380,000 years old. Back then, the universe was a sea of hot plasma, so hot atoms couldn't form. Photons traveled mere inches before being caught by charged particles. As the universe expanded and cooled enough, protons and electrons combined into hydrogen atoms for the first time. The fog lifted, the universe became transparent. Light could travel freely. This was the epoch of recombination. The first photons to escape are what we observe today as the cosmic microwave background, CMB, radiation. It is everywhere, filling every cubic inch of space. Even the snow on an old analog TV contains about 1% of this ancient light. More importantly, it marks the edge of everything we can see. You can never see beyond this horizon because the earlier universe was opaque, like the sun's interior. Events before 380,000 years ago are forever hidden. The CMB is the earliest brick wall. It defines the observational limit. The universe's fate, seemingly this wall is receding. Each second, light that has traveled 13.8 billion years plus 1 second reaches us. Thus, the observable universe's radius grows by 1 light second each second. About 186,000 miles of new space entering view. Per day, we gain about 16 billion miles of observable universe. But consider this. While the screen enlarges, the light sources are being carried away by expansion. A galaxy that emitted a photon 13 billion years ago may now be 30 billion light years away. We see its ancient form, not its current position. This mismatched screen zooming in, actors moving back, is the daily reality of cosmological observation. A smooth beginning, yet the CMB tells us a crucial fact. The early universe was incredibly smooth, with temperature variations of mere millionths of a degree. These tiny ripples eventually seeded today's galaxies and us. Beyond the bubble, based on CMB measurements, the universe is nearly uniform on the largest scales. This means no matter where you start, the composition and proportions are similar, like extremely well-mixed cake batter. Every spoonful is the same. Thus, if our observable universe holds about 2 trillion galaxies, another region of the same size beyond almost certainly holds a similar number. This pattern extends region after region. More strikingly, if space is nearly infinite and maintains this uniformity, then within any given volume, every possible arrangement of matter will repeat somewhere. This sounds metaphysical, but the conclusion is mathematical. Finite microscopic arrangements plus infinite volume equals inevitable repetition. The ultimate conclusion. Inevitable repeats. Thus, the most startling conclusion emerges. Repetition is unavoidable. Think of a deck of cards. Shuffle it infinitely, and identical orders will eventually recur. The universe operates similarly with atoms and their configurations. Thus, in extremely distant regions, there must exist another you reading these words. This is not metaphor, but literal deduction. In those regions whose light will never reach us, quantum mechanics has arranged matter in every possible way, including one identical to your current state. So somewhere, another you stops reading now. Somewhere you were never born. Somewhere you live on an Earth with a completely different history. Mathematics even gives a sense of scale. These copies are about 10,115 meters away. This number is so vast that writing it out in full would require more digits than there are atoms in the observable universe. Yet if space is truly infinite, such distances remain finite. So somewhere, another you just realized this fact. Farther away, another you realizes the previous, you just realized it. But what if conditions differ beyond? Recent observations suggest our cosmic region might be unusually sparse, a cosmic void with below-average galaxy density. If true, beyond the observable boundary might lie more crowded space, more galaxies, more black holes, more violent activity, or perhaps the opposite, near empty desolation. Older theories trace back to the initial instant, a brief, frenzied period of cosmic inflation might have torn the whole into many pocket universes with different properties, different physical constants, different particle families, even unfamiliar physical laws. Our textbooks would fail beyond our pocket. We find everything normal here, simply because we happen to live in this particular pocket's recipe. What if the universe isn't infinite? An expanding infinite universe presents a seeming paradox. How can infinity grow larger? Mathematics answers you can't. Infinity plus any finite number remains infinity. Multiply it by 2 still infinity. You can't add to what already contains everything. Yet observation clearly shows space stretching everywhere. The resolution lies in discarding the intuition that expansion means adding to infinity. A better description, the scale factor is increasing. Imagine an infinite grid where each square is 1 inch wide. Now stretch the entire grid so each square is 2 inches wide. The grid remains infinite. The squares remain countless. But the distance between any 2 points is doubled. This is the essence of cosmic expansion. It doesn't add infinity to infinity. It increases the unit scale of the grid, causing all distances to grow proportionally. Thus, galaxies 100 million light-years apart today were only 50 million light-years apart when the universe was half its current size. The Big Bang everywhere. If the universe is infinite now, it must have been infinite at the Big Bang. The Big Bang wasn't an explosion from a point outward, but infinite space beginning to expand at every location simultaneously, filled with energy. In other words, the Big Bang happened everywhere. It has no center, no edge, no outside. Any location can claim to be the center, because from everywhere, the expansion looks the same. This perspective explains why we see nearly the same universe in all directions, and why we find no edge or center. Infinite matter, finite density. If the universe contains infinite matter and energy, why don't we have infinite density? Density is total mass divided by volume. Even if numerator and denominator approach infinity, if they grow at the same rate, the ratio can remain finite. Thus, the universe can place infinite matter in infinite space, while maintaining a finite average density, about a few hydrogen atoms per cubic meter. The ultimate repeats in a truly infinite universe. Any event permitted by physical laws will occur infinitely many times. Not just another you, but every story in every version. Tragedies and victories, beauty and cruelty, all play out somewhere. If this feels unsettling, consider the finite universe possibility. A universe with an end forces harder questions. What lies outside the boundary? Can space truly have an edge? What happens if you try to cross it? These questions lead many scientists to prefer models where space is vast or nearly infinite. While conceptually challenging, it sidesteps what's outside questions. Combined with the latest CMB measurements, we either face an infinite universe or one so large we detect no curvature. The simplest explanation: space extends infinitely in all directions. Thus, the growth we see isn't like adding rooms to a house, but loosening an already infinite grid. What drives the stretch? Put plainly, the universe manufactures new space from the quantum vacuum at a rate that would humble any factory on Earth. Roughly every second, the observable universe's volume grows by about 1,078 cubic meters. This number is so large that counting to it would take far longer than the universe's current age. The quantum vacuum isn't nothing. It's a ceaselessly bubbling foam of virtual particles, constantly appearing and vanishing in tiny time intervals. This is quantum fluctuation. It endows every point of space with energy. The truly counterintuitive part: this vacuum energy manifests through gravity. Unlike matter's gravity, which pulls things together, vacuum energy produces repulsion. It pushes space outward. More space gives more vacuum energy, gives faster expansion, gives more new space. When this feedback loop runs unchecked, you get runaway inflation. In the earliest instant, this process ran wild. Space expanded faster than light could travel through it. This didn't violate relativity. Nothing moved through space faster than light. Space's fabric itself stretched faster than light could cross it. During that time, a region smaller than a proton could inflate to nearly basketball size in an unimaginably brief interval. This sounds like science fiction, but quantum mechanics ledger demands it. Borrow energy from the vacuum and repay it quickly enough. During inflation, the universe borrowed vast energy from the vacuum. To mass-produce space, then used expansion itself to balance the books. It's like taking a loan to buy a money printer, then using the printed money to repay the loan. The mechanism worked too well. It only needed to create enough space to solve certain cosmological puzzles. But it over-delivered, producing far more territory than necessary. Our entire observable universe is but a tiny patch on this vast inflated fabric. Dark energy takes over. Though early inflation stopped, today's expansion continues, now driven by another player: dark energy. It constitutes about 68% of the universe's total energy content. Its behavior almost mimics vacuum energy, pervading space uniformly and providing repulsive gravity, accelerating the expansion. As volume grows, new dark energy appears to fill the new space. This seems to create energy from nothing, apparently violating conservation. The resolution lies in gravity's ledger. Gravitational potential energy is negative. As space stretches, the gravitational binding energy between matter decreases. This increasingly negative energy can offset the positive energy of newly created dark energy. The result? The universe continuously generates new space, while keeping the total energy balance near zero. Evidence in the static. We don't need to seek evidence in distant myths. It lies in humble places. When you switch channels on an old analog TV, a tiny fraction of the snow and noise comes from the universe's earliest light. The answer is in that static. In 1964, at Bell Labs, Penzias and Wilson struggled to eliminate a persistent hiss in their antenna. They changed directions, calibrated equipment, even cleaned off pigeon droppings. But the noise remained. It turned out not to be a malfunction, but the echo of creation. They had accidentally detected the cosmic microwave background, the afterglow of the Big Bang. Due to the universe's ongoing expansion, this ancient light has been stretched and cooled, not just 2.7 degrees above absolute zero. This discovery earned them the Nobel Prize and provided the most direct evidence that the universe is expanding. Moreover, this background light doesn't just exist. It carries the fingerprint of expansion in its spectrum. Initially about 30 degrees Celsius visible light, stretched first to infrared, then to microwave, finally to radio waves. Meanwhile, the whole sky's brightness is flat as a mirror, uniform to within hundred thousandths of a degree. This perfectly matches inflation's prediction. Without an early, extremely rapid stretch to smooth irregularities, we should see huge temperature variations, but we don't. Quantum seeds of structure? So where did the tiny remaining fluctuations originate? The answer lies at the quantum level. Inflation stretched subatomic quantum fluctuations to cosmic scales. These faint energy ripples later became the seeds for galaxies and stars. In other words, you can read these words today. Because quantum uncertainty was amplified to macroscopic scales by the universe itself, mapping the ancient light through code and Planck satellites. We've mapped these temperature variations in exquisite detail. The distribution of angular scales matches inflation's theoretical curve almost point for point. Based on this ancient microwave light, we can not only see, we can measure. Geometrically, space is nearly flat within measurement precision. In composition, ordinary matter is only about 5% of the total. Dynamically, expansion rate and universe's age can be inferred within narrow ranges. More intuitively, the data gives a Ing sense of scale. The entire observable universe today was once compressed into a volume roughly the size of a beach ball. This compression wasn't stuffing things into a box. Space itself was tightly squeezed. That beach ball wasn't a container for the early universe. It was the universe at that time. No outside, no surroundings, just that compressed space-time. Then it began expanding and cooling, yielding today's starry sky. The 1998 surprise, acceleration. To find what energized this expansion, scientists turned to a steadier cosmic candle, Type Ia supernova. In 1998, two teams used these standard candles to measure how expansion should slow under gravity's pull. The logic was simple. Compare these supernovas' actual brightness with their standard brightness, add redshift data, and calculate their true distances. But the plotted results completely reversed expectations. Distant supernovae were dimmer than predicted, meaning they were farther away than standard models calculated. In other words, the space the light traveled through was more stretched than we thought. The universe wasn't breaking, it was accelerating. This discovery also won a Nobel Prize and introduced us to a new character, dark energy. Dark energy's dominance. Dark energy now constitutes about 68% of the universe's mass energy, more than all ordinary matter combined, and more influential than dark matter. Its weirdness, it doesn't clump or dilute. Matter thins as volume grows, but dark energy's density remains nearly constant during expansion. Thus, the larger the universe, the greater its total influence. Early on, matter and radiation dominated. Dark energy was background. As matter was stretched increasingly thin, dark energy's repulsive effect gained prominence, becoming dominant about 5 billion years ago. Since then, the universe entered its accelerated era. If this trend continues, more distant galaxies will recede faster than light can catch up, eventually vanishing forever from the observable universe. What is this unseen pusher? The prime candidate is vacuum energy, the baseline fluctuation of quantum fields in seeming emptiness. But naive estimates from quantum field theory suggest the vacuum should be packed with enormous energy, about 10,120 times larger than observed. This is arguably the worst prediction in physics history. So either we're missing a key piece of the quantum puzzle, or nature has some mechanism canceling almost all vacuum energy, leaving just enough to drive acceleration. Alternatively, some propose dark energy is a cosmic field that changes over time, or suggest rewriting gravity's laws on cosmic scales. Whichever path, the current conclusion is the same. Our ignorance about it parallels ancient humans gazing at lightning, but it continues shaping the universe's fate. Inflation, the initial frenzy. Many ask, if expansion once outpaced light, what happened? This didn't violate, nothing moved faster than light. The objects weren't moving. Space's scale itself was accelerating. Shortly after the Big Bang, the universe entered inflation. Distances doubled and redoubled in unimaginably brief intervals. Faster than light could cross them. Think of two ants on a rapidly inflating balloon. However they crawl, they only grow farther apart. By orders of magnitude, inflation enlarged the universe by at least 1,026 times, all within about 10 to 32 seconds. For comparison, light travels only 30 centimeters in 1 nanosecond. Driving this frantic stretch was a quantum field called the inflation field. Unlike many fields that settle at zero energy, it was trapped in a high-energy false vacuum, like water held high, supplying space with continuous energy for a brief period. Exponential growth is deceptive, initially unnoticeable, later explosive. It not only smoothed early irregularities, making the sky nearly uniform, but also flattened cosmic curvature and amplified tiny quantum fluctuations into seeds for all future structure. Your galaxy, your star, even the atoms in your body, trace back to random ripples from that moment. A disturbing possibility, eternal inflation. If inflation happened once, why only once? The quantum field that drove initial inflation likely still lurks behind the scenes. Given the right conditions, it could trigger new rounds of exponential stretching. New inflation bubbles could nucleate anywhere, anytime, expanding near light speed. rewriting everything in their path. Inside these bubbles, new physical laws would operate. Our atoms would disassemble. Familiar rules would instantly fail. Worst of all, we'd receive no warning. For inflation theory, the most striking is our universe might be just one bubble in an infinite bubble sea. As you read this, countless other universes may be born elsewhere, each with different natural constants, particle families, even physical syntax. This sounds like science fiction, but it's a logical extension of inflation theory. If it happened once, quantum fluctuations will make it recur on a grander stage. Thus, bubble upon bubble is blown, each inflating, cooling, potentially nurturing its own galaxies and planets. Our universe is merely one among them. In other bubbles, gravity might be stronger, stars would quickly collapse into black holes. Gravity might be weaker, matter might never clump. Some bubbles lack electromagnetism, chemistry is impossible. Others remain eternally inflating, never cooling enough for atoms. Most bubbles are too barren for life, but in a truly infinite bubble sea, even the most improbable combinations will appear somewhere. Thus, the anthropic principle finds new explanation. We don't inhabit a fine-tuned universe because it was made for us, but because only such a universe can give rise to observers. In other words, we see it because it allows us to exist. Philosophical implications. If there truly are infinite universes, then every possible experience plays out somewhere. Choices you didn't make are made by another you. Tragedies you avoided befall another version of you. Dreams you never lived flourish in another reality branch. Thus, uniqueness is diluted to near meaninglessness. The weight of choice is distributed across countless parallel scripts. The challenge of verification. By definition, other bubbles lie outside our cosmos. They send no light, leave no gravitational traces. We cannot directly prove their existence or measure their properties. Hence, many scientists remain skeptical of the multiverse. If it's not testable, it isn't strictly science. Yet inflation's mathematics strongly points toward eternal inflation and bubble production. The same equations that successfully explain early cosmic expansion naturally lead to ongoing inflation and bubble formation in vaster space. Moreover, the CMB's subtle statistical patterns highly match inflation's predictions. While this doesn't directly prove other bubbles exist, it suggests we might live within the best evidence supporting a multiverse. Hidden dimensions? You might still imagine our universe as a 3D bubble, but newer physics, hence reality, might be stranger. What if inflation occurs in directions we cannot perceive? String theory requires 9 spatial dimensions. Besides our familiar 3, 6 are tightly curled up, hidden here and now, too tiny for particles to detect. We might be like ants walking on a garden hose, only moving forward, backward, mistakenly thinking the world is one-dimensional. If these extra dimensions exist, they might expand alongside our 3D space. Thus, where is the universe expanding? Gets another answer. Our 3D space might be a membrane stretching into a higher dimensional bulk. The accelerated expansion we observe might be this membrane warping in higher dimensions. Bolder brain world models propose. All particles and forces except gravity are confined to our 3D membrane. Only gravity leaks into extra dimensions, explaining its unusual weakness. If there are parallel membranes in higher dimensions, they could be nearby in directions we cannot see, occasionally colliding. Some models interpret our Big Bang as a collision between membranes. The CMB might be the afterglow of that impact. On super long time scales, membranes might repeatedly meet, each collision hitting a reset button, initiating a new cycle of cosmic evolution within our 3D space. There are even stranger speculations. While our 3D space seems static, extra dimensions themselves might be inflating, or some dimensions grow while others shrink. Thus, the overall volume might not change, but our 3D slice appears to widen. Currently, these remain hypotheses. We cannot directly touch extra dimensions. The Large Hadron Collider seeks signs of particles disappearing into hyperspace, but no conclusive evidence yet. This might mean extra dimensions don't exist, or that they're more tightly curled than we thought. Still, string theory's math suggests extra dimensions might be essential for describing reality. The universe's shape. Even without hidden dimensions, 3D space's own shape could redefine where expansion goes. General relativity allows three geometric fates. Flat like an infinite plane, zero curvature. Positively curved like a sphere. Negatively curved like a saddle. Observations indicate our universe is either flat or so close to flat we can't measure, but flat doesn't necessarily mean infinite. A piece of paper is flat, but you can roll it into a cylinder, or connect edges to form a torus donut. Locally flat, globally closed, and finite. If space is self-closed in some way, expansion simply enlarges this closed structure's size. It isn't entering an external warehouse. It's growing into a larger version of itself. If space were torus-shaped, light could circle around, returning to its origin. We might see the same distant galaxy in different directions. The CMB should show repeating patterns from light wrapping around. Astronomers have searched for such markers in cosmic maps, finding no solid evidence. This suggests either the universe is much larger than our observable patch, or on currently detectable scales it lacks such self-closed structure. In other words, the universe might be a donut, but one so vast light hasn't had time to loop around. Space-time, the unified view. Stepping back, we see space and time are united as 4Ds. The shape question becomes more complex. Expansion doesn't just stretch space. It alters the space-time relationship. In the early universe, everything was extremely compressed. Time passed differently than today. The concept of simultaneous loses universal meaning across vast distances. As space stretches, time stretches too. Thus, a seemingly paradoxical scene. Some distant galaxies recede faster than light, but they aren't racing through space. Space itself carries them away while stretching times. From their perspective, they are almost stationary. It's the rulers and clocks between us and them that change. Relativity tells us, from any location, the expansion looks the same. Every observer feels at the center. Everything else recedes. No one has a privileged reference frame. No external origin exists. Measurable time dilation. This stretching isn't abstract, it's directly measurable. For example, a nearby supernova might brighten and fade over 3 weeks. But if the same supernova occurs in a faster receding, more distant galaxy, the process appears in slow motion to us. Reason: the light carrying the event information is stretched during its journey. Not only is its wavelength stretched, but the time between light pulses is lengthened. Thus, we see a time-dilated version, a concrete number. Light from the observable edge has redshift factor, approximately 10, meaning events that appear 10 times slower than local processes. This also explains why the universe's age is perspective dependent. From our view, it's about 13.8 billion years old. But if you stood in those receding galaxies looking back, our region would appear much younger. In the early universe, not only was space more compact, but time was too. Processes requiring billions of years today might have occurred on much shorter timescales then. The first stars, galaxies, black holes were born in that rhythm. Furthermore, expansion shatters our intuition about simultaneity. Events you perceive as simultaneous might not be for a distant observer. There is no universal, now only local nows. As dark energy's influence strengthens, this time-stretching effect will amplify. Future observers will see more extreme time delays, until those events appear almost frozen. The universe's future, based on current understanding, expansion will increasingly dilute matter and energy. Over immense time, the universe approaches heat death. Temperature differences vanish. Usable energy is exhausted. The world becomes nearly uniform void near absolute zero. A rough timeline. 100 billion years from now, last stars die. No new stars form. Universe enters degenerate era, dominated by cold stellar remnants. 1,034 years. Protons may decay. Atoms and planets disintegrate. Only electrons, positrons, and photons remain, floating and expanding emptiness. 10,100 years. Black holes become the only significant energy source. They slowly evaporate via Hawking radiation. Supermassive black holes might last approximately 10,100 years. When the last black hole evaporates into faint radiation, the universe reaches maximum entropy. No temperature differences, no chemistry, no computation, no life. Unless dark energy's nature changes fundamentally, accelerated expansion steers the world toward this icy fate. The Great Dissolution. In the nearer future, the impact is still profound. As space-time stretches faster, distant galaxies will drop from our observable range. They aren't destroyed. They recede so fast their light can never reach us. Later, even the CMB will be stretched to undetectable wavelengths. Future astronomers will see only our local group, surrounded by boundless emptiness. Key evidence for the Big Bang will vanish. In contrast, a Big Rip endgame only occurs in more extreme scenarios. If dark energy's strength keeps rising, acceleration could overwhelm all known forces, from gravity and electromagnetism to the strong nuclear force binding atomic nuclei. The universe would be torn apart from within. But regardless of the specific end, one thing is certain. So-called empty space isn't empty. The vacuum is a quantum furnace. On the smallest scales, it boils with virtual particles appearing and vanishing too quickly to catch, yet leaving real physical traces everywhere. The quantum vacuum. Imagine using a microscope with resolution far beyond atomic nuclei. Zooming down to the Planck scale, approximately 10 to 35 meters, the seemingly smooth space-time fabric would churn like boiling soup. Geometry fluctuates between instants. Virtual particles borrow energy from the vacuum. The uncertainty principle dictates the more they borrow, the faster they must repay. Electron-positron pairs appear and annihilate. The whole process might last Y-21 seconds. Heavier virtual particles live even shorter lives. All quantum field theories allowed virtual particles take turns on this seemingly empty stage. It is this unseen quantum furnace that determines how cosmic expansion gradually stretches the fabric of space-time. This isn't metaphysics. It leaves fingerprints detectable in the lab. The classic example, the Casimir effect. When two metal plates are brought extremely close in a vacuum, only virtual particles with wavelengths shorter than the gap can fit between them. Longer wavelength ones are excluded outside. This asymmetry creates pressure pushing the plates together, a force that can be directly measured. You are literally touching the quantum vacuum's pressure. The vacuum catastrophe, but where quantum foam truly impacts cosmology. It should contribute to vacuum energy density. When physicists calculate, the result is absurdly large. Theoretically, the universe should expand far faster than observed. The theoretical value exceeds dark energy's actual strength by 10,120 times. This is one of theoretical physics' most embarrassing failures. Either our understanding of the quantum world lacks a crucial piece, or the universe has some mechanism canceling almost all vacuum energy. If we could solve this vacuum catastrophe, we might uncover dark energy's true nature. Perhaps the tiny, uncancelled remnant is the dark energy driving accelerated expansion. Maybe the universe suppresses most quantum foam, permitting only a tiny fraction. Or perhaps our calculation method is fundamentally flawed. Bolder ideas suggest a vacuum might be filled with hidden fields or extra dimensions leaking vacuum energy. Even the concept of nothing might be an illusion from our limited perspective. Loop quantum gravity proposes space is a network woven from discrete loops. String theory views it as the outcome of interacting strings in higher dimensions. Whichever side you take, the conclusion points in the same direction. Space isn't an empty background. It's a structured medium. Expansion might be stretching this medium, not creating more space from nothing. The Big Rip scenario. Even with our limited understanding of the vacuum, its implications for the future are in. If acceleration keeps strengthening, what happens? One extreme scenario, the Big Rip, approximately 22 billion years from now, dark energy could grow strong enough to progressively all natural binding forces. The universe wouldn't slowly cool over trillions of years. It would rapidly in a short time. A rough countdown. 1 billion years before Big Rip. Galaxy clusters are torn apart. 200 million years before, galaxies like the Milky Way are shredded. Stars are dragged from gravitational embrace. 30 minutes before, planetary systems' gravity fails. Earth is flung from the sun. The moon escapes Earth. Final minutes. Molecular bonds break, gases dissipate. Oceans boil not from heat, but from intermolecular distances stretching beyond force endurance. 10 to 12 seconds before atomic nuclei disintegrate, strong nuclear force surrenders completely. The final instant, even distance and time intervals, the metrics describing our world may lose meaning. Of course, this all depends on whether dark energy continues strengthening. If it remains constant, the big rip won't occur. The universe would suppress acceleration, but gradually approach heat death. Current data supports basic constancy, but precision is insufficient. Future, finer supernova observations will keep asking, is it changing? If strengthening is confirmed, a specific countdown can be calculated. Einstein's blunder vindicated. In 1917, soon after completing general relativity, Einstein encountered a problem. His equations naturally predicted an expanding or contracting universe. No static, unchanging universe allowed. But the prevailing belief then was a static, eternal universe. To match this observation, he added a new term, the cosmological constant, lambda. He interpreted it as a tiny energy inherent to the vacuum, a gentle, repulsive force exactly balancing gravity, keeping the universe static. This patch seemed reasonable and held for about a decade, until Hubble used Mount Wilson's Large Telescope to measure distances and velocities of remote galaxies, finding they were generally receding, with farther ones moving faster. The universe wasn't static, it was expanding. This was the original prediction of Einstein's equations before he added lambda. So he discarded the cosmological constant, calling it his greatest blunder. Ironically, decades later, the 1998 supernova observations brought the cosmological constant back. We found expansion isn't uniform, it's accelerating. To drive this acceleration, we need an energy density that's uniform, fills space, and produces repulsive gravity. Its effect is identical to the cosmological constant. In other words, if dark energy is the cosmological constant, then Einstein's initial intuition was remarkably prescient. His reasoning was wrong, but his direction was right. The vacuum catastrophe persists. Looking closer, vacuum energy's value is very small, but not zero. About 10 to 10 joules per cubic centimeter. This seems negligible, but multiplied by the observable universe's volume, it exceeds all matter and radiation combined, directly dominating the universe's late evolution. The problem: quantum field theory calculates vacuum energy 10^120 times larger than observed. This is the famous vacuum catastrophe. Either our quantum world understanding lacks a key piece, or nature has a mechanism canceling almost all vacuum energy. Some propose dark energy isn't constant, but a field slowly evolving over time, dynamic dark energy, to circumvent the catastrophe. For now, the simplest cosmological constant model remains the best fit to astronomical data. Hubble's legacy, returning to Hubble's night of observation, the scientific community was still debating whether spiral nebulae were within the Milky Way. Hubble used Kephi variable stars as standard candles, measuring these fuzzy objects' distances to millions of light years and beyond, clearly establishing them as independent galaxies. Then he plotted these galaxies' distances and spectral redshifts on a graph, revealing a clear pattern. The farther the galaxy, the faster its recession. This is Hubble's law. Initially, he thought galaxies were flying through space like explosion fragments, but that would place Earth at the center, violating the Copernican principle. The more accurate explanation, space itself is stretching. Think of galaxies as dots on a balloon's surface. Inflate the balloon, and every dot sees the others receding. The farther, the faster. But no dot is the center. Hubble's law thus became the first solid evidence for cosmic expansion. Its proportionality constant, the Hubble constant, describes how fast recession speed increases per unit. Hubble's original distance calibration confused variable star types, so his initial value was too high, implying a universe younger than Earth. Later calibrations corrected the age to reasonable range, but the linear relationship held. Farther equals faster receding from nearby galaxies to the most distant visible. This curve not only advanced astronomy from 2D sky maps to a measurable 3D cosmos, but also pushed a key question to the forefront. Will expansion continue forever? The cosmic density threshold. The answer depends on how much stuff the universe contains. Physically, there's a critical density line, determining whether the universe expands forever or eventually recollapses. Intuitively, expansion pulls everything apart. Gravity pulls everything back. It's a contest of mass per unit volume. Exceed critical density, gravity eventually wins. Expansion slows, stops, reverses toward a big crunch. Falls short, expansion forever dominates. The world dilutes toward near nothingness, heading for heat death. Exactly at critical density, expansion speed approaches zero asymptotically. Like a ball thrown exactly at escape velocity, it coasts toward infinity, speed nearing zero. What's mind-numbing? This cosmic knife-edge density appears almost empty, equivalent to about 5 hydrogen atoms per cubic meter. Yet this very value determines the ultimate fate of all galaxies, stars, planets, and us. For decades, measuring the universe's true density was considered cosmology's holy grail. It sounds simple. Add up all mass, divide by volume. But implementation is messy because most cosmic stuff is invisible. Galaxies' rotation curves gave it away. Outer stars orbit too fast. To prevent them flying off, the required gravitational mass is about 5 times the visible stellar mass. Thus, this invisible mass was dubbed dark matter. It doesn't emit, absorb, or reflect light. It only tugs the visible world via gravity. We can only infer its presence through its effects on stars, gas, and galaxy clusters. Including dark matter, the universe's total density is only about 30% of critical density. By this accounting, the universe should expand forever, slowly approaching heat death. But dark energy's entrance rewrote this conclusion. Dark energy not only raises the total energy density, but crucially, it carries negative pressure. In Einstein's equations, such components push space-time to accelerate outward. In other words, regardless of ordinary matter's amount, with dark energy present, expansion runs ever faster. Combining current observations, our universe is roughly 27% dark matter, 68% dark energy, 5% ordinary matter. Considering dark energy's negative pressure, this recipe places the universe almost exactly at critical density, as if finding delicate balance between different geometric fates. The flatness problem. This raises the flatness problem. Why is density so fine-tuned to critical? In most evolution models, density should quickly deviate from critical, either too large, leading to crunch, or too small, leading to dispersal. Maintaining just right requires initial conditions fine-tuned to countless decimal places. Cosmic inflation offers a way out. During that exponential stretch, any initial curvature was smoothed away. By inflation's end, the universe naturally approached critical density. But then, the coincidence problem arises. Why do we live precisely when matter and dark energy are roughly equal? Perhaps this is observer selection bias. Only in eras where structures can form but haven't been diluted beyond recognition can observers like us arise to look up and ask questions. The multiverse perspective. Zooming out, the single universe assumption might not hold. In eternal inflation scenarios, our observable universe is just a small patch within a vastly larger inflating region. Quantum fluctuations occasionally trigger new bubbles elsewhere. Universes inflate, cool, grow galaxies and planets. Some bubbles have stronger dark energy, expanding faster. Others are matter-rich, evolving slower. Some have already recollapsed into big crunches or head toward big rips. Add quantum mechanics' many worlds interpretation. Nearly every microscopic branching spawns a parallel history. Thus, the number of parallel universes is unlimited. New branches born every moment. In some branches you close this diary. In others you witness its saying. In many more, you continue living against an accelerating cosmic backdrop. Evidence is hard to find because these universes are causally disconnected. Scientists have searched the CMB for fingerprints of bubble collisions, but no conclusive findings yet. Nonetheless, the multiverse concept has changed how we discuss expansion. For our local space, expansion is overall growth. For the larger structure, it might be just one layer of a more complex phenomenon. Personal implications, returning to information and identity, the question becomes more personal. Every thought in your mind, every memory, is essentially a specific arrangement of matter and energy. Cosmic expansion is slowly these arrangements. This seems to destroy information, yet physics says information cannot be truly destroyed. The holographic principle offers a perspective. All information within a volume can be encoded on its surrounding boundary. As the universe grows, the boundary's surface area increases, adding storage capacity. Complexity still has room to expand. Quantum entanglement also plays a role. It maintains correlation between particles across vast distances, hinting that information is more about relationships than absolute position. The problem: accelerated expansion severs causal links. Regions once able to communicate will eventually recede faster than light relative to each other. Information gets locked inside isolated cosmic bubbles, unable to interact. Macroscopically, cosmic history remains imprinted in large-scale structure and the CMB. Microscopically, local information becomes irretrievably scrambled. The far future perspective, pushing the view to the ultimate future. As dark energy continues stretching space-time, the CMB will be redshifted beyond detection. Distant galaxies will drop from the cosmic horizon one by one. Future astronomers looking up might see only a few nearby galaxies, detect no expansion, see no Big Bang afterglow. they would reach a seemingly simple yet completely wrong conclusion. The universe is static and eternal. By approximately 150 billion years from now, dark energy will push most galaxies beyond the horizon. Their light will be stretched to wavelengths longer than the observable universe, effectively vanishing from observation. To that era's observers, only our local group remains visible. Meanwhile, the Milky Way and Andromeda, with their satellite galaxies, will merge into one isolated giant elliptical galaxy, floating quietly in empty nothingness. To them, this single ball of starlight is the entire universe. Simultaneously, the CMB will exit the stage. As space keeps stretching, this primordial radiation's wavelength will be stretched longer than the observable universe, becoming undetectable by any instrument. Thus, all evidence pointing to a cosmic beginning will be lost. Even the redshift distance relation won't be visible. Without seeing distant galaxies, Hubble's law cannot be discovered. No direct proof of space stretching exists. Consequently, their observed universe will appear completely static. Based on this, future scientists would likely develop a different cosmology, believing that single giant galaxy has always existed in an infinite, unchanging void. They might find it hard to imagine the universe was once filled with billions of galaxies, receding from each other in an expanding cosmos. In other words, they will inhabit a universe stripped of its own history. This loss of perspective will deepen further. Future observers will also lose key clues about early nucleosynthesis. The nuclear reactions forging the first elements ended billions of years ago. Their traces linger only in the chemical composition of the oldest stars, becoming increasingly difficult to identify. The result, an epistemological crisis. Intelligence and technology may remain advanced, but the universe offers almost no hints about its own nature. The methods remain the same, but with too little evidence, conclusions will be skewed. This forces us to reflect. Could our current cosmic knowledge also be limited by our era? Might we have already missed crucial information only early observers could see, now erased by expansion? Perhaps civilizations born right after the Big Bang witnessed scenes we can never see. The ultimate end, the analogy extends to the final end. As space continues expanding, processes supporting life will eventually become unsustainable. Gas becomes too thin. Gravity can no longer pull it into clouds. Star formation ceases entirely. Existing stars exhaust their fuel and fade. Black holes slowly evaporate via Hawking radiation. Ultimately, the vast void holds only sparse elementary particles. The universe approaches perfect equilibrium. Should observers still exist then, their world would be even more deceptive. No stars, no galaxies, no structure, just sparse particles floating in infinite emptiness. They would naturally assume the universe was always this monotonous, unable to imagine its former richness, from abundance to nothingness. This pushes the question, where is the universe expanding to the extreme? Reframing the question. This question presupposes a seemingly reasonable, yet unnecessary premise. Expansion must have a purpose, a destination, an external space to fill. The reality is more direct. Expansion is the reason. It provides a dynamic stage where transient, complex structures can emerge. galaxies, planets, even life, appear precisely because this stage can enlarge. Without expansion, the universe would either promptly collapse or remain forever in a monotonous state. But this returns us to the starting point. In a universe that manufactures space, generates time, and simultaneously serves as its own stage, what does "where is it expanding to" even mean? The final answer, when you ask where the universe is expanding, you assume a pre-existing exterior. As a balloon needs air, a city needs countryside. But the universe isn't a balloon. The universe is space. When space expands, it isn't entering some external place. It is, while expanding, creating the very concept of outside. Thus, there is no stage independent of the universe, because the meaning of external is defined by the universe itself. This isn't a language trap or an imagination shortcoming. It's the structure of reality. Before expansion, inside and outside held no meaning. Expansion simultaneously creates more space and generates the rules that make spatial relationships possible. The universe isn't expanding to somewhere. It is, by becoming more universe, accomplishing expansion, not invading some supposed non-universe. A deeper understanding. Following this realization, our understanding of expansion shifts from mechanical process to deeper insight. Expansion resembles a reality bootstrapping itself, pulling itself from nothingness to complexity. Every cubic inch of newborn space opens new possibilities for matter, energy, structure, and complexity. The universe isn't growing towards some predetermined end. It is advancing toward a state capable of infinite potential. We aren't passengers on a cosmic ship being carried somewhere. We are part of this self-creating process. Our consciousness, questions, and curiosity are the universe's way of knowing itself. The expansion we observe isn't separate from us, because we are the expansion. We are patterns of complexity, emerging from space, time, matter, and energy self-organizing, able to question our own meaning. From this perspective, the apparent paradox resolves, and a deeper mystery emerges. Since the universe can manufacture space and time, being both stage and audience, then existence might be stranger than any science fiction. Perhaps we live in a self-creating, self-sustaining process, without beginning or end, inside or outside. The universe is expanding into itself, making room for infinite possibilities, and for beings like us to find our place. Conclusion. Looking back on this journey of inquiry, the question led us through inflation and dark energy, multiverses and quantum foam, the beginning and end of time. The most valuable answer lies before us. The universe is increasing possibilities. We are making sense of it. Thus, arriving here, we realize we never faced merely a cold cosmic model. It is both the expanding void and the entire stage of our birth, thought, and doubt. Like the initial question, if the universe truly has rules, is it a product of order or a chance occurrence of chaos? Perhaps we won't find the answer soon, but that doesn't matter, because the search itself is the meaning of human existence. In endless time, we have only just turned the first page. The holographic universe. Information as the ultimate reality. As we push deeper into the nature of cosmic expansion, we encounter perhaps the most radical proposition yet. that our three-dimensional reality may be a holographic projection from a two-dimensional surface at the cosmic horizon. This isn't science fiction, but a serious theoretical framework emerging from black hole physics and quantum gravity. The mathematics suggests that all the information contained within any volume of space can be encoded on its boundary. As the universe expands, this informational boundary grows, creating new storage capacity for reality itself. Every cubic centimeter of new space that comes into existence carries with it not just vacuum energy, but informational potential, new states for quantum possibilities to manifest, quantum entanglement and cosmic connectivity. Across the expanding vastness, quantum entanglement maintains mysterious connections between particles that have become separated by billions of light years. This spooky action at a distance that Einstein famously questioned now appears to be fundamental to the fabric of reality. The very expansion that creates separation between galaxies may be weaving an invisible quantum network connecting all things. Recent experiments with quantum teleportation over increasing distances suggest that entanglement relationships can persist even as space stretches between particles. The cosmic expansion isn't necessarily breaking quantum connections, it's scaling them up to astronomical proportions. We're discovering that the universe may be far more interconnected than its expanding geometry suggests. The role of consciousness in cosmic evolution. A more speculative but profound extension considers the role of consciousness in the expanding cosmos. The anthropic principle that the universe's laws appear fine-tuned for life takes on new dimensions when we consider that conscious observers may play an active role in determining reality. Quantum mechanics has long struggled with the measurement problem, how probabilities become definite outcomes when observed. In an expanding universe filled with countless conscious beings, each act of observation may be contributing to the crystallization of reality from quantum possibility. The expansion that creates new space also creates new opportunities for consciousness to emerge and interact with the quantum substrate of reality. We're not just passive observers of cosmic expansion. We may be participants in the universe's ongoing self-creation. The physics of nothingness. Why there's something rather than nothing. At the most fundamental level, cosmic expansion forces us to confront the mystery of existence itself. Quantum field theory reveals that what we call empty space is actually a seething foam of virtual particles popping in and out of existence. The cosmic expansion appears to be drawing new reality from this quantum potentiality. The question, why is there something rather than nothing, transforms when we understand that nothing in the quantum sense is unstable. The vacuum wants to produce particles. Empty space wants to expand. The very laws of physics seem to favor existence over non-existence. Cosmic expansion may be the macroscopic expression of this fundamental tendency for reality to emerge from possibility. The multiverse as ecological system. The concept of multiple universes evolves from mere theoretical possibility to a rich ecological framework. Different cosmic regions with different physical constants might interact through subtle quantum channels or higher dimensional bridges. Our universe's expansion could be influenced by its environment and a broader multiverse landscape. Some theories suggest that new universes can bud off from existing ones, like cosmic reproduction. The expansion we measure might contain echoes of our universe's parent cosmos. The cosmic microwave background could hold faint imprints of previous cosmic generations, waiting to be decoded in future observations. Time's arrow and cosmic expansion. The expansion of space appears intimately connected with the direction of time. The thermodynamic arrow of time, while we remember the past but not the future, may be rooted in cosmic expansion. As space grows, it creates new possibilities for energy to become more disordered, driving the increase of entropy that gives time its direction. If the universe eventually stops expanding and begins to contract, would time run backward? Most physicists think not, but the question highlights the deep connection between cosmic dynamics and our experience of temporal flow. The expansion of space may be the ultimate clock, kicking out the rhythm of cosmic history. The universe as a learning system. Some theoretical physicists and cosmologists have begun exploring the idea that the universe might be a kind of self-organizing, learning system. The laws of physics themselves could be evolving, with cosmic expansion providing the time for this evolution to occur. The emergence of complexity from quarks to consciousness might be the universe's way of exploring its own possibilities. In this view, each conscious being becomes a sense organ through which the universe comes to know itself. The expansion that creates the stage for this cosmic self-discovery becomes more than just a physical process. It becomes the unfolding of cosmic meaning and purpose. The information theoretic universe. The most cutting-edge approaches to fundamental physics suggest that information may be more fundamental than matter or energy. The universe might be essentially computational in nature, with cosmic expansion representing the increasing computational capacity of reality. Each new cubic meter of space provides more memory for the cosmic computer to run its algorithms of physical law. This perspective transforms how we view cosmic history. The Big Bang wasn't just the beginning of matter and energy. It was the initialization of the cosmic computational process. The expansion we measure is the scaling up of reality's processing power, with galaxies, stars, and planets as emergent patterns in this cosmic computation. Cosmic evolution and the future of complexity. As we look to the far future of cosmic expansion, the conventional story is one of eventual heat, death, and dissolution. But more nuanced views suggest that complexity might find ways to persist even in an expanding, cooling universe. Advanced civilizations of the distant future might learn to harness the energy of black holes or manipulate the fabric of space-time itself. The expansion that seems to threaten cosmic vitality might actually enable new forms of organization we cannot yet imagine. Just as life on Earth transformed the planet in ways unpredictable from its initial conditions, intelligence distributed across galaxies might learn to engineer cosmic evolution on the grandest scales. The ethical dimensions of cosmic responsibility. If we take seriously the possibility that consciousness plays a role in shaping reality, then our ethical responsibilities extend beyond Earth to the cosmos itself. How we choose to develop as a species might influence not just our planet, but the evolutionary trajectory of the universe. The expansion that gives us room to grow also gives us space to make choices that could echo through cosmic history. This perspective transforms environmental ethics into cosmic ethics, preserving biodiversity, cultivating wisdom, advancing knowledge. These become not just human concerns, but contributions to the universe's ongoing self-creation. We become stewards not just of a planet, but of a cosmic process. The spiritual implications of an expanding universe. Throughout human history, spiritual traditions have grappled with questions of transcendence, meaning, and our place in the cosmos. The scientific understanding of cosmic expansion provides a new context for these perennial questions. The universe's ceaseless growth mirrors spiritual concepts of infinite possibility and endless becoming. Many mystical traditions speak of reality as fundamentally interconnected, a vision that finds resonance in quantum entanglement and the holographic principle. The expansion of space becomes a physical manifestation of the infinite creativity of existence. Our own moments of insight and understanding become participation in this cosmic unfolding. The ultimate question: why expansion at all? After exploring cosmic expansion from every angle, from quantum mechanics to consciousness, from the multiverse to spiritual meaning, we return to the most fundamental question: why does the universe expand at all? Why didn't it remain static or begin collapsing immediately? The answer may lie in the deepest principles of reality. Expansion may be necessary for complexity to emerge. A static universe might remain featureless and simple. A contracting universe might collapse before life could appear. The particular expansion history we measure seems exquisitely tuned to allow for galaxies, stars, planets, and life. This brings us full circle to where we began, contemplating a universe with no outside, generating its own space as it grows. But now we see this process as rich with meaning and possibility. The expansion isn't just something the universe does, it may be fundamental to what the universe is, a creative process of self-realization, exploring infinite possibilities across endless space and time. The human role in the cosmic story. As we stand at this particular moment in cosmic history, able to understand the expansion, to trace it back to its beginnings, to project it into the far future, we realize that we are not just observers but participants. Our scientific inquiry, our artistic creation, our moral choices all become part of the universe's ongoing story. The expansion that began 13.8 billion years ago has produced beings who can look back and understand the process. In us, the universe has become self-aware. We are the cosmos contemplating itself, the universe awakening to its own nature. This recognition carries profound responsibility and opportunity. How we choose to use our knowledge, how we navigate our future, how we relate to each other and to the cosmos. These choices matter on a cosmic scale. We are not just living in an expanding universe. We are the expanding universe, becoming conscious of itself. The never-ending journey of discovery. As we continue to probe the mysteries of cosmic expansion, new questions continually emerge. Future observations with more powerful telescopes, more sensitive detectors, and more sophisticated experiments will undoubtedly reveal surprises that challenge our current understanding. The journey of cosmic discovery has no end. Each answer reveals deeper questions. Each horizon crossed opens new vistas to explore. The expansion that carries galaxies away from us also carries the future toward us, filled with possibilities beyond our current imagination. We stand at the beginning of humanity's cosmic journey, not the end. The understanding we've gained so far is just the first glimpse of realities far stranger and more wonderful than we've yet conceived. The expanding universe is not just our home, it's our inheritance, our responsibility, and our ultimate destination as we continue the never-ending journey of discovery. The quantum roots of cosmic evolution, from nothingness to everything. To truly understand the nature of cosmic expansion, we must venture into the realm of quantum gravity. At this scale, space-time itself ceases to be a smooth, continuous background, but becomes composed of discrete quantum units. The latest loop quantum gravity theory proposes that space is woven from incredibly tiny loop-like structures, with time emerging as the evolutionary manifestation of this network. Within this framework, the essence of cosmic expansion transforms into the evolution of quantum space-time structures. Each Planck time, y-43 seconds, the quantum fabric of space-time reconfigures itself, generating new connections and creating new space. The cosmic expansion we observe is essentially the macroscopic expression of this fundamental process. The quantum structure of the vacuum, the eternal dance of creation and annihilation. Quantum field theory reveals that the vacuum is far from empty. Even at absolute zero, the vacuum teems with quantum fluctuations. Virtual particle pairs continuously emerge from nothingness, only to annihilate within incredibly brief moments. This process obeys the Heisenberg uncertainty principle, allowing energy to be borrowed for extremely short durations. Cosmic expansion is profoundly connected to these quantum fluctuations. When space expands, it's essentially stretching the ground state of the quantum vacuum. New space means new patterns of quantum fluctuations, new virtual particle pairs, new possibilities. Expansion isn't creating space from nothingness, but rather reorganizing the structure of the quantum vacuum. The cosmological constant problem, physics' most precise wrong prediction. One of the greatest mysteries in modern physics is the cosmological constant problem. Quantum field theory calculations predict vacuum energy density, Y, 120 times larger than observed values. This discrepancy is so enormous that it's been called the worst theoretical prediction in the history of physics. Solving this problem may require completely rethinking our understanding of the vacuum. Perhaps vacuum energies at different energy scales cancel each other out, leaving only a tiny net effect. Or there might be some undiscovered symmetry that precisely cancels the vast majority of vacuum energy. Alternatively, our quantum field theory framework might need fundamental revision at cosmological scales. The quantum origin of the inflation field, a phase transition of spacetime. While cosmic inflation theory successfully explains many observational facts, the origin of the inflation field itself remains mysterious. Recent research suggests that the inflation field might originate from quantum gravity effects. During the Planck era, quantum fluctuations in space-time might have triggered a phase transition, sending the universe into exponential expansion. This phase transition resembles superconductivity or water boiling, but occurs within the fabric of space-time itself. The inflation field might represent the collective behavior of spacetimes, quantum degrees of freedom on macroscopic scales. When the universe cooled below a certain critical temperature, the quantum structure of spacetime underwent reorganization, releasing enormous potential energy that drove inflation. Quantum entanglement and spacetime geometry. In recent years, theoretical physicists have discovered profound connections between quantum entanglement and spacetime geometry. This discovery, known as the E=EPR conjecture, links Einstein-Rosen bridges, wormholes, with quantum entanglement. In this framework, the connectivity of spacetime might be determined by patterns of quantum entanglement. Cosmic expansion could correspond to the expansion and complexification of entanglement patterns. When new space is created, it comes with the establishment of new quantum entanglement relationships. This perspective offers a fresh viewpoint for understanding the quantum wholeness of the universe. The holographic principle. Cosmic encoding on a two-dimensional surface. The holographic principle might be the most radical proposition in modern physics. It suggests that all information needed to describe a spatial region can be encoded on its boundary. Just as a hologram stores three-dimensional information on a two-dimensional surface, our three-dimensional universe might be a projection from a two-dimensional surface. If this principle holds true, then cosmic expansion corresponds to the expansion of this holographic boundary. The creation of new space means new information storage capacity. The universe's history, structure, and even its physical laws might all be stored on this ever-expanding boundary. The quantum nature of time, from eternity to flow. Time has always been a mystery in fundamental physics. In general relativity, time is dynamical. In quantum mechanics, time is absolute. In our experience, time has direction. Cosmic expansion might be intimately connected to all these aspects. Loop quantum cosmology proposes that time itself is quantized. Cosmic evolution corresponds to changes in quantum states along internal time. Cosmic expansion then becomes the manifestation of this quantum evolution. The arrow of time might arise from the universe's evolution from a highly ordered quantum initial state toward more complex states. Observational signals of quantum gravity. Although quantum gravity effects are generally considered far beyond current experimental detection capabilities, cosmological observations might provide an indirect pathway. The inflationary period of the early universe amplified quantum fluctuations to cosmic scales, and these fluctuations ultimately formed today's large-scale cosmic structures. By precisely measuring polarization patterns and temperature fluctuations in the cosmic microwave background radiation, we might detect primordial gravitational waves carrying information about the universe's earliest physics. Next-generation cosmology experiments like Light-BRD and CMBS-4 promise breakthroughs in these areas. The string landscape and multiverse. String theory proposes a vast landscape. The number of possible vacuum states is estimated at YIV. Each vacuum state corresponds to a universe with different physical constants. Our universe might be just one point in this enormous landscape. In this framework, cosmic expansion might represent transition processes between different vacuum states. Inflation could be our universe's process of finding a stable position within the strained landscape. The small value of the cosmological constant might not stem from some profound principle, but simply because only such universes can produce observers, causal patches, and observational limits. Even if the universe is infinite in its entirety, any observer can only access a finite region, their causal patch. This patch is determined by the distance light can travel within the universe's age. As the universe expands, distant galaxies recede beyond the horizon, disappearing from our observations. This fact has profound implications for our understanding of the universe. We can only ever see part of the universe, and this part is constantly changing. Conclusions we draw today based on the observable universe might be completely invalid on larger cosmic scales. Quantum cosmology and the initial state problem. What were the universe's initial conditions? Why did the universe begin in such a highly ordered state? These questions are central to modern cosmology. Quantum cosmology attempts to describe the entire universe using quantum mechanics, thereby addressing these initial state problems. The Hartle-Hawking proposal suggests that the universe's quantum state is determined by its values on the boundary, without a specific initial time. In this framework, the universe is self-contained, requiring no external initial conditions. Cosmic expansion becomes the natural evolution of this quantum state. The quantum nature of dark matter. While dark matter's existence has been confirmed through its gravitational effects, its essence remains unknown. Dark matter might not consist of particles from the Standard Model, but rather new physics beyond it. Axions, weakly interacting massive particles, WIMPs, sterile neutrinos are all candidates. The properties of these particles might be closely related to their role in cosmic structure formation. Dark matter might not be completely dark. It might influence visible matter through extremely weak interactions. The dynamics of dark energy. Observations show that dark energy drives the universe's accelerated expansion, but its nature remains mysterious. The simplest explanation is the cosmological constant, but other possibilities exist. Quintessence, modified gravity theories, vacuum phase transitions, etc. Future observations from facilities like LSST, Euclid, and the Roman Space Telescope will distinguish between these models by measuring cosmic expansion, history, and if dark energy is found to be dynamical, it would fundamentally transform our understanding of cosmic destiny. The quantum origin of cosmic structures, galaxies, galaxy clusters, cosmic webs. All large-scale structures originate from quantum fluctuations in the early universe. These tiny fluctuations were stretched to cosmic scales during inflation, then gradually grew under gravitational influence. By studying the statistical properties of these structures, we can understand the characteristics of primordial fluctuations, thereby inferring the physics of the inflationary era. Current data have already constrained inflationary models to a relatively small range, but many questions remain unanswered. The philosophical foundations of cosmology. The study of cosmic expansion raises profound philosophical questions. What is reality? Is the universe unique? Are physical laws necessary or contingent? What is our place in the cosmos? The answers to these questions not only affect our understanding of the universe, but also influence our contemplation of our own existential meaning. Science and philosophy converge in cosmology, jointly exploring the nature of existence. Computational cosmology and numerical relativity. With growing computational power, numerical simulations have become crucial tools in cosmological research. The entire process from quantum fluctuation generation to galaxy formation can be simulated in supercomputers. These simulations not only help us understand existing data, but also predict new phenomena. When observations diverge from simulations, it often heralds the discovery of new physics. Multi-messenger astronomy and cosmology, gravitational wave detection, neutrino observatories, cosmic ray observations. These multi-messenger approaches are transforming our understanding of the universe. These new observational windows provide information different from electromagnetic radiation, helping us build a more complete cosmic picture. For instance, gravitational waves can directly detect violent cosmic events like black hole mergers and neutron-star collisions. These events are not only interesting in themselves, but can also serve as standard candles for measuring cosmic expansion. Relic particles from the early universe. The high-temperature, high-density environment of the early universe might have produced some stable relic particles, like magnetic monopoles, cosmic strings, domain walls, etc. Although these particles are rare in today's universe, their detection would directly verify early universe theories. Various current dark matter detection experiments like Xenon, LZ, and Panda X are searching for these potentially existing relic particles. Any discovery would tremendously advance our understanding of the early universe. Future challenges in cosmology. Despite cosmology's tremendous progress in recent decades, many challenges remain. The nature of dark matter and dark energy, verification of inflation, integration of quantum gravity, testing the multiverse, etc. Addressing these challenges requires theoretical innovation, technological advancement, and international collaboration. Next-generation observational facilities like the Extremely Large Telescope, Square Kilometer Array, and James Webb Space Telescope will provide unprecedented data. The unification of cosmology and fundamental physics. Cosmology is becoming a testing ground for fundamental physics. The extreme conditions of the early universe provide energy scales unattainable in Earth laboratories. By studying cosmic evolution, we can test various unifying theories. String theory, loop quantum gravity, causal set theory. All quantum gravity candidates make testable predictions. Future cosmological observations might provide the first experimental evidence for quantum gravity. The human significance of cosmology. Finally, the study of cosmic expansion holds not only scientific significance, but also profound human meaning. It transforms our understanding of time, space, and existence, redefining humanity's place in the cosmos. We know the universe had a beginning. We know it's evolving. We know we're made of stardust. These realizations not only satisfy our curiosity, but also inspire our imagination, motivating us to continue exploring this mysterious and beautiful universe. Epilogue, the never-ending exploration. Standing at this frontier of knowledge, looking back on the journey from Hubble's discovery of cosmic expansion to today, we feel both humble and hopeful. Humble because we know that Compared to the entire universe, our knowledge remains insignificant. Hopeful because we know that exploration is endless. Every answered question opens new questions. Every solved mystery reveals deeper mysteries. Cosmic expansion is not merely a physical process. It's also a symbol of humanity's expanding cognition. Just as the universe continuously expands its boundaries, human understanding constantly breaks through its own limitations. In this sense, we are not just observers of the universe, but instruments of the universe's self-awareness. The road ahead remains long, but every step is filled with the joy of discovery. From quantum foam to cosmic horizons, from time's beginning to space's edges, the journey of exploration has just begun. In this expanding universe, our adventure never ceases.